Let's look at the area between two curves. We've seen that the integral from a to b of f of x dx represents the area of the region between the curve y equals f of x and the x-axis for x between a and b. In the same way, the integral of f of y dy, well, it's what you'd expect. It represents the area of the region between the curve x equals f of y and the y-axis for y between a and b. So for example, find the area of the region between the graph of x equals y squared plus 1 and the y-axis for -2 less than or equal to y less than or equal to 2. Okay, here's what that curve looks like. It's a parabola. So the integral is going to be y squared plus 1 dy from -2 to 2. That just represents the area of this region. The area of the region between x equals y squared plus 1 and the y-axis for y between -2 and 2. Okay, so we integrate y squared plus 1 dy from -2 to 2. We get y cubed over 3 plus y from -2 to 2. Plug in 2, we get this. Plug in -2, we get this. And this all simplifies to 28/3. The area of the region below y equals g of x and above y equals f of x for a less than or equal to x less than or equal to b can be represented by this integral, the integral from a to b of g of x minus f of x dx. So for example, if we have some curve y equals g of x, and we have some curve y equals f of x, and let's say this is a over here, and let's say this is b over here, this integral, the integral of g minus f, just represents the area of this region between y equals g of x and y equals f of x, a less than or equal to x less than or equal to b. For example, let's find the area of the region under y equals x plus 3 and above y equals x squared for -1 less than or equal to x less than or equal to 1. Here's what the region looks like. So we want to find the area of this region for x between -1 and 1. So like this and like this, and we want to find the area of all of that region. Okay, that's going to be the integral from -1 to 1 of x plus 3 minus x squared dx. And here's why. This is the graph of y equals x plus 3. This is the graph of y equals x squared. This first part of the integral, x plus 3, that's going to be all of this area. It's the area under y equals x plus 3. And this, what we're subtracting, basically what we're subtracting is this integral, the integral from -1 to 1 of x squared dx. That's going to be just this part over here. Okay, so when you take the entire area and subtract off this part, here's what you end up with. You just end up with this part over here. Okay, so anyway, when we evaluate this integral, when we integrate with respect to x, we're going to get x squared over 2 plus 3x minus x cubed over 3. And let's see, this is going to be, it's going to be from -1 to 1. So this would be from -1 to 1. Plug in 1, we get this. Plug in -1, we get this. And it all simplifies to 16/3. Find the area of the region bounded by y equals 5 minus x squared and y equals x squared minus 3. Okay, these are two parabolas. Y equals 5 minus x squared, y equals x squared minus 3. So it looks like it's going to be the top function, 5 minus x squared, minus the bottom function, x squared minus 3. So our integral is going to look like this. The integral of 5 minus x squared minus 3. It's the top minus the bottom. But we don't know the limits of integration. So we need to find where these curves intersect. 5 minus x, x squared minus 3, we can do that. So we solve it like a system of equations. Move the 3 to the other side, x squared to the other side, we end up with 8 equals 2x squared. In other words, x squared equals 4, so x equals plus or minus 2. And note, those appear to be the points where the graphs intersect at x equals plus or minus 2. So those will be our limits of integration. We're going to integrate from -2 to 2. So we have the integral from -2 to 2 of 5 minus x squared minus 3 dx, which simplifies to 8 minus 2x squared from -2 to 2. Integrate, okay, from -2 to 2, and we're going to get, when we plug in 2, this. When we plug in -2, we get this. Okay, 16 minus -16 is 32. Minus 16/3 twice, we end up with that. So we end up with 64/3. That's the area. Let's find the area of the region between y equals sine x and y equals cosine x for 0 less than or equal to x less than or equal to pi over 2. Okay, this one's tricky because notice over here, cosine x, the blue function, is on top. And notice that over here, between 0 and, between this point and pi over 4, pi over 2 over here, this is really pi over 4 over here. Notice that from pi over 4 to pi over 2, the red function, sine x, is on top. So here's what we need to do. For this first integral, it's going to be the top minus the bottom, cosine x minus sine x. And for the second one, it's going to be sine x minus cosine x. So here we have it, cosine x minus sine x. X goes from 0 to pi over 4. Sine x minus cosine x. X goes from pi over 4 to pi over 2. Let's integrate these. Antiderivative of cosine minus sine, it'll be sine plus cosine, as x goes from 0 to pi over 4. And integrate sine minus cosine. Antiderivative of sine is negative cosine. Antiderivative of negative cosine is negative sine. So that's why we get this from pi over 4 to pi over 2. Simplify all of this, and we end up with 2 root 2 minus 2. So we talked about the area between y equals g of x and y equals f of x. Okay, in the same way, we can have the area between x equals g of y and x equals f of y. Okay, let's say from A to B. The area of the region to the left of x equals g of y and to the right of x equals f of y, for a less than or equal to y less than or equal to b, is just going to be the integral of g minus f dy from A to B. And when we're calculating areas like this, any area that's below the x-axis or to the left of the y-axis, that doesn't get counted negatively when we're finding the area between two curves.